the other one as well.
Right, okay, merge sort. Right, so merge sort. It actually doesn't do any sorting. It's quite an amazing algorithm. Alright, so what we do, we use another assumption, the same assumption that insertion sort used at the start. If we've got a list with one item in it, we can assume that list is sorted. Now there's a classic algorithm that is used for merging data that you can't store in the computer's memory, and that's called merge file sorting. So you have two sorted sets of data stored on a tape, and you read in from tape one item at a time, and you compile a new tape with the data items in order. And this is what merge sort does, but it does it all in memory. So what we've got to do is take our list and turn it into 6 separate lists that contain one item, and then we can say, hey, the job is now just to merge these lists that are already sorted together. So we have to have a process, and that process is splitting the list into sublists. So we start off with a list of 6. So the first phase of merge sort will be to create 2 lists. We don't even look at the numbers. We don't care about the numbers at all. We create lists, 2 lists. This is going to go horribly wrong on the board, but I'll try my best to fit it on. With 3 data items in each. So the first part of the merge sort is to keep doing this, and this is why it's easy to put together recursively, is because what your job is to say, give me a list, I'll split it into 2 lists. I've now got 2 lists, which I can split into 2 lists. The really nice thing about these sort of divide and conquer algorithms is you can do these 2 jobs independent of each other, because you're not looking at them. Which means if you've got multiple processors, you can take advantage of doing this split on one processor, doing this split on another processor. So it's scalable. If you've got a supercomputer, which I know none of you lot have got, like some of the Chinese ones that have got 2 million CPUs, you could do the merge sort quite quick on something like that. So we're just going to split these 2. Right, they've got an odd number. So we just go, alright, split it into a 1 and a 2. So 17, sorted. 2 and 3, well, we don't know about that. We don't know what the numbers are. Split this one to a 20. That's a sorted list. And then we've got 9 and 10. So we've got 2 lists that we still got to split. So we're going to split them. So we just keep doing a split. They ought to call it the split and merge sort. But they don't. So we won't. Just call it merge sort. Drew the box a bit weird there, but there you go. Right, so we've now got to a point where we have got 6 independent single item lists, which we can hand on heart say they independently are sorted. So the next phase of the merge sort is to do the merging. So all we do is we take pairs of lists and we just take the first item from each and say which is the right order. I'll put that one first, put that one next. So we're going to take this pair and we're going to say, okay, look at the first item from this list. Well, there's only one. We need to make a list with 2 items in it. Which one goes first? Well, the 2 goes first. That list is now empty. There's nothing else to look at. We're still looking at that item, so we say, oh, well, let's put that one next. That list is empty. We've exhausted those 2 lists, so we can stop. We can then take another pair. So we've got this pair. And we're going to do the same thing. We need 2 spaces, so let's make 2 spaces up. Read the first item from each list. I'm saying it in that way because it's what we do later on. So 3 and 20, 3 smaller, so we'll put that one first. That list is exhausted, no more comparisons to make, so we can just take what's in this list. One more pair of lists to put together, those 2. So we need 2 items for that. Read the items from each, compare them. Okay, 9 goes first, then we'll put the 10. So that's the first phase of merging gone. We've ended up with 3 lists, so we need to merge 3 lists. We can't do 3 at once, so we're just going to do a pair. So we're going to take this pair, and we're going to say, right, okay, there's 4 items, so let's make space. The only problem with merge sort is that it uses twice as much space as you originally had. It's not an in-place sorting method like bubble sort and insertion sort. They didn't use any extra space, but this one you need twice as much space. Okay. Right, so we've got 4 places. Right, so we look at the first item in each. And we say, okay, looking at the first item, 2 and 3, which one's smaller? Well, the 2's smaller. So what we do is we then move that along, so we look at the second item, and we compare the 2 pointers. It's all about pointers. Pointers are quick on a computer. 17 and 3. Well, 3's smaller, so let's now move to the next one in that sub-list. We've got 17 and 20. 17 smaller. We've exhausted that list, so we can actually just dump the contents of this. You don't even need to look at any more numbers, although there's only 1 item. So we're now in this situation where we've got 2 sub-lists. So this is the Big Daddy movement. We're going to get the original sorted list. It looks like we're doing a lot of work, which admittedly, if I was going to sort 6 numbers, I would not use merge sort. If I was going to sort 6 million numbers, I would use merge sort. Okay? Right, so I need space for 4 and 2. So I need, let's try and make this not look too naff. I need space for 6. So again, I'm going to look at the first item from each sub-list. 2 and 9. 2 is smaller. Move along in that list that we just took that number from. 3 and 9. 3 is smaller. Move along. 17 and 9. 9 is smaller. Move along in that one. 10 and 17. 10 is smaller. Oh, we have got to the end of the list. So I just wrote the 10 down and I went, oh no, I've finished with that list. So again, we've got a simple little bound check that we do, nothing complicated. Now I've got 2 items left, but I don't need to do any more comparison. And this is where merge sort starts winning. Okay, it is better than Quicksort in most cases, because we reduce the amount of comparisons. So we say, you know what, I'm going to dump them. And hopefully, unless I've made an absolutely enormous cock up, I've got a list at the bottom that's in order. Okay, it is a beautiful algorithm, merge sort. The implementation is not too bad. All you've got to do is, if you have not got at the start a list with 1 item, you say, let's go and merge it again and split. As soon as you're down to 1 item in your 2 sub-lists, you can start doing the build up again. I've got the algorithms on the intranet, so I'm not going through the actual algorithms. They're on the intranet. I've given you pseudocode of them. Okay, so that's merge sort. So it's n log n in terms of time complexity, and it's 2n really in terms of space complexity. So you need twice as much space as you originally had, because what you end up doing is you keep flicking from one set of data to another and keep moving them around, and then end up with a final list at the end. It's a great algorithm. I love merge sort.
Is there a worst case scenario for that?
The worst case scenario is if you have to look at every single item. You know, like when we got to there and we went, oh hey, we've exhausted one of the lists, so we can just dump. There's no more comparisons. The worst you're going to get is where you have to make comparisons all the way up to the end, like we did on the first couple. That would be your worst case. So you'd have to have a peculiar set of data for that to happen. Okay, but it's a great algorithm. About that long, the code, when you code it up. Alright, but it is fast and it is quicker than merge sort. There's those videos, isn't those of robots sorting numbers, sorting the balls. Remember I can't remember what that was on there. Some weird thing. Yeah, I put a link on the internet. But it shows you, I think they did a Quicksort merge sort on that one. And it looks like Quicksort's kicking ass, and then the merge sort just goes boom at the end, because it has to do all this prep at the start. So it's preparation. But, it's a nice algorithm. Right, so let's have a look at the other quick one, which gets the name Quicksort because it's quick. Quicksort, there are a couple of different ways of implementing it. Some are more hideous than others. But Quicksort, the easiest way to implement Quicksort is recursively, but you do get a problem with all recursion: depth of the stack. You can only have so many function calls that before you start having to unroll them. Okay, so if you get too much data, a straightforward Quicksort won't work. There are loads of adaptations for Quicksort. But let's just, I'll do it in 6 numbers again because it takes forever to do it. And it's all about manipulating pointers, Quicksort. Right, so we start with a list. Now, what we are trying to achieve is the exact same thing that merge sort and insertion sort use. We want to split this list from one big list into sublists. And again, because we can work independently on these are highly parallel. Okay, the implementations that you can use for these algorithms. So we want to get down to a single list on its own so we can say, right, I'm sorted. And that's the premise it uses. I'll talk about the efficiency bit we were talking about when Sean went to the toilet when I've got to the end. Right, okay, so we start by looking at the entire list. And the key thing is we have a couple of pointers, left and right pointer. And a pivot value. In a lot of algorithms, people just ignore the pivot value. Okay, but I'm keeping that in because this is what we're doing. What we want to do is we want to subdivide the list. It doesn't really do a sort, Quicksort. It just divides the list into a number which we call the pivot, and then what we're going to do, everything that's bigger than the pivot we want in the right hand list, everything that's smaller than the pivot we want in the left hand list. Okay, so we start like this. And we look at these left and right pointers and we say, okay, the pivot, we could mathematically try and use some sort of heuristic to work out where the best place to start is, but that takes time. So what we do is just say, let's just pick the left-hand item in the list, and that's what we're going to pivot around. So we set the pivot to the left, and we just say, right, looking at the left and right pointers, are the numbers in the right relative positions? So we're going ascending again. So we say 5 and 10, yeah, they're in the right place. So what we do, and this is the key of Quicksort, we move the pointer that isn't associated with the pivot inwards. So the right pointer moves in. Again, quick operation, just subtracting 1. And we just keep comparing. Now this time, we've got an issue, 3 and 5 are not relatively in the right order. So we're going to swap them. So we're going to take the 5 and we're going to put that here. Now 5 is the pivot value, so we move the pivot. Got to make sure we do that. And we put the 3 in the space it's been vacated. And that's the comparison complete. So what we do is we move the pointer not associated with the pivot inwards. If you don't do this right, you end up looking at the same numbers twice and it totally breaks. Right, so we then start a process again. We say, right, okay, looking at the left and right pointers, are the numbers in the right relative positions? No, they're not, so we need to swap them. So the 5 comes over there, the 7 goes there. The pivot has moved, so we keep the P with the pivot value. If, when you're doing these, if you just want to write down P equals 5, so you do not forget. Okay. Right. We've done the swap, we add our comparison, we now move the pointer in that isn't with the pivot. Again, 5 and 9, compare. Oh, they're in the right relative order. Move the value not in with the pivot. Compare again. 5 and 4. Ooh, not in the right relative order. So we're going to swap them. This is what merge sort doesn't do. It's swapping is a complex. There's 3 steps to swapping. So swaps cost. So we do that, we swap them round, we move in the pointer not associated with the pivot. That's our stop condition. When the left and right pointers become aligned to the same value, we have gone through the list and stopped. Now what we end up doing every time we do this in Quicksort, so that's one pass of the Quicksort, we've actually put the 5 in the correct place. Everything to the right is bigger, everything to the left is smaller. What we've now ended up with are 2 sublists. I'm not going to go through the whole process. Okay. We've got 2 sublists, which we can now perform Quicksort on. So I will Quicksort this list, and I will Quicksort this list. And I can do it independently, i.e. on separate threads or processors. My stop condition is when I get down to a single item. Then I can say, that's it, don't need to keep recursing and doing quicksort. So every time you run quicksort, it will, unless you haven't got a list to sort, which does happen, you will run 2 more quicksorts and 2 more quicksorts. Okay? In terms of that, you're going to use a lot of stack. So there is a limit to how big this can be, and with big data sets you can come into problems with quicksort. But there is optimizations. Obviously there's a lot of work doing a lot of comparisons. Merge sort didn't do this, but quicksort does. So to reduce the number of comparisons, in a real world example, you might be, I don't know, you're sorting 10 billion data items. Once we get these lists down to 10 or so items, it's quicker to use one of the dumbass sorting methods like insertion sort or bubble sort. So instead of doing a pure quicksort and going down to one data item is sorted, we say we've got 10, let's use another method, the quick. Okay, so there's optimizations you can do in order to do that. But you can see straight away there's a lot more comparisons going on. Merge sort didn't do much comparison at all. Remember this, the merge at the start where we split it into ones, that didn't compare anything, just split the list up. And then the other bit, you're only comparing those numbers a few times. In quicksort, you might have a situation where you're swapping continually. Okay, but it's again it's n log n in terms of time. It's an in-place sort, so it's memory efficient compared to merge sort. So sometimes that becomes your factor. If you're short on memory and you can't afford to duplicate a list, merge sort might not be suitable. They're relatively similar in terms. Merge sort normally, I think some merge sorts worst case scenarios are still as quick as quicksort's best. But it becomes down to memory efficiency, your decision to use one or the other. You'll find that in a lot of libraries, I think the .NET library, the sort routine is actually a quicksort routine. If anyone's, none of you use that for your stuff, did they? But yeah, no, there's a quicksort routine in there, built in. Okay, right. So that's the basic structures. Remember, you can't compare the search methods with the sorting methods, but they will ask you to compare linear and binary in the same way all the time. They'll always talk about, you know, what are the prerequisites. Remember, prerequisites means what do we need in place in order for this to work. So, but binary, got to be sorted. Linear doesn't give a monkeys. But we can do some efficiency with linear if it is sorted. Bubble, insertion and merge and quick, they are sorting the data. So if you want sorted data for your binary search, you have to do the sort first. Or, as you add data items, you maintain sort order, which is a whole nother kettle of fish. That depends on how you're storing your data. Okay, right, I'll leave it there, and I've said okay again, I can't help it. I bet I can't turn the camera off now because it's locked. Well, that's not as bad as some of them videos are horrendous. And people have taken the mickey out of me for it as well. If I will put things on YouTube,